This is the first of two videos on error analysis. This is covered in Wessel's Chapter 2. After viewing this video, first you will know how to report your data using the right number of significant figures, and you'll also know how to report the uncertainties or errors of your data. The second main objective you'll have for this video is knowing how to compute the uncertainties of a function of quantities which themselves are uncertain. So in this video, we'll cover sums as well as general functions. Now, the first aspect that you should always keep in mind when you're working with data or manipulating data is that just about every quantity that you work with is associated with or has errors or uncertainties. And certainly every data or every measurement that you make has uncertainty or error. So let's talk about what error is. So more specifically, error is often used to describe variability of a measurement associated with a mistake. And that mistake could be from the instrument itself, that is, if the instrument is not working correctly, it will give rise to errors. It may be associated with the user of the instrument, or it may be, for example, associated with an error in a calculation needed to make or manipulate a measurement. In contrast, an uncertainty is the variability of what you might measure that results that aren't associated with mistakes, but they too can be associated with the instrument depending on its accuracy. So if the instrument is used correctly and it's functioning to specifications, it has a certain accuracy, and that accuracy determines an uncertainty in the measurement that it would make. Uncertainties are also associated with natural processes or conditions of the experiment. Okay, so we often report our data in terms of its measured values and in this case we'll say the measured value is x, and we'll report the uncertainty in terms of plus and minus a delta x. Those are our errors or uncertainties. For example, if we make a measurement of temperature, say we measure 310 degrees, we would report it as 310 degrees plus or minus the uncertainty or error. And I'll just say 10 degrees, for example. Now, the uncertainty is very closely related to the accuracy of our measurements. That is, delta x represents the accuracy of x. Hence, the last significant figure we report our data to is of the same order as delta x. So in the example above, we had an uncertainty of 10 degrees, and therefore we correctly reported our measurement as 300 as 10 degrees. So the uncertainty is on the order, has an order of magnitude of 10 degrees C. So the lowest significant figure that we have, or the last significant figure, is in the tenths place in our temperature measurements. Now, just to remind you, let's go over some significant figures. Let's look at the number 311.1 degrees C, for example. And that has 4 significant figures, of course. And we could also write that as 3.111111 times 10 to the 2 degrees C. If we wanted to write the same number in 3 significant figures, we would write 311 degrees C, or 3.11 times 10 to the 2. If we were to write it in terms of 2 significant figures, that would become 310 degrees C, or 3.1 times 10 to the 2. And certainly if we wanted to write that in terms of 1 significant figure, that would be, we would round to the nearest hundredths in that case, and that's 300 degrees C, or 3 times 10 to the 2 degrees C, just to remind us what significant figures are. So let's look at uncertainties of functions. And let's consider the sum, S, being x plus y. And if x, we know, has an uncertainty, so we might make x, when we measure it, has a measurement value of x sub 0, and we know it has an uncertainty of delta x, and y is equal to our measured value plus or minus delta y. What then is our uncertainty in S? Now, if delta x and delta y represent the full possible range of x and y, then the full possible range of the sum is the sum of delta x and delta y. So in that case, we would write S as equal to x naught plus delta x plus y naught plus delta y, and that is equal to the sum of the measured values, which gives the best estimate of S, that's x naught plus y naught, plus the uncertainty of S, which is delta x plus delta y. Okay, and that's a special case, again, if delta x and delta y represented the full possible range. But in practice, delta x and delta, it's often better or more appropriate to write delta x, or to describe delta x and delta y as the most likely variability about the measurements x naught and y naught. So in that case, it's better to describe delta x and delta y as the standard deviation of the measurement. Or oftentimes we'll write STD for short. So in that case, again, if delta x and delta y are standard deviations, then the variance of S is given by the sum of the variances of x and y. That is, the variance, which is the square of the standard deviation of S, is equal to delta x squared plus delta y squared. And that's what defines, well, actually, the standard deviation is defined as the square root of the variance. When I write 3 bars, that means that it's describing a definition. And likewise, the standard deviation of the sum is simply the square root of the sum of the variances. And so that describes the errors of sums. I realize that we haven't yet defined what standard deviation and variance is. We'll get to that in a couple of days, but for now you should just remember that they represent the most likely variability of a measurement about a determined value, a measured value. Now, the last topic I'd like to cover in this one video, I'll end after this, is just describing the uncertainties of a general function. So more generally, if we have a function of x and y, it has a variance described again by delta f squared, and that's equal to the partial derivative of f with respect to x times the standard deviation of x, and that's all squared, plus the partial derivative of f with respect to y times the standard deviation of y squared. So this is the general way to describe the variance of a function of 2 variables. And we'll look at some examples in the next video of how we would apply this.